We humans have always been explorers. From navigating uncharted seas to conquering the skies, our thirst for discovery knows no bounds. But there's one frontier that dwarfs all others, the cosmos. Our journey begins right here, on planet Earth. A tiny blue marble, orbiting an average star we call the Sun. Our Sun is just one of billions of stars in the Milky Way galaxy. The Milky Way, in turn, is just one of billions of galaxies that populate the observable universe. It's a snapshot of the universe as it appears to us, right here, right now. Imagine standing on a ship in the middle of the ocean. The horizon marks the limit of what you can see. The observable universe is similar. It's the horizon of our cosmic ocean, the boundary set by the speed of light and the age of the universe. Light, the fastest thing in the universe, takes time to travel across vast distances. When we look at distant galaxies, we're seeing them as they were billions of years ago. The universe is about 13.8 billion years old. This distance defines the edge of the observable universe. Now, here's the catch. Just because we can only see a certain distance doesn't mean that's all there is. It's like our ship on the ocean. Just because we can't see beyond the horizon doesn't mean the ocean ends there. The universe is likely much, much larger than what we can observe. But the observable universe, with its billions of galaxies and countless stars, provides us with ample material for exploration and discovery. To truly grasp the mind-boggling scale of the observable universe, we need to understand one crucial concept. The universe is expanding. That's right, space itself is stretching, like dough rising in an oven. This expansion isn't happening within some larger void. It's the very fabric of space-time that's growing. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move apart, even though they haven't moved on the surface of the balloon itself. Similarly, galaxies are like the dots on the expanding balloon of our universe. The light from distant galaxies has to travel through this expanding space to reach us. As the universe expands, the light waves traveling through it get stretched out as well. This stretching of light waves is called redshift. Think of it like a sound wave. As an ambulance siren moves away from you, the sound waves stretch out, making the pitch lower. Similarly, as light waves from distant galaxies travel through expanding space, they get redshifted, their wavelengths stretched towards the red end of the electromagnetic spectrum. The more distant a galaxy is, the more its light has been redshifted by the time it reaches us. By measuring this redshift, astronomers can calculate how much the universe has expanded since the light left that galaxy. This helps us estimate the distance to that galaxy. The light from the most distant galaxies we can see has been traveling towards us for almost the entire age of the universe. But here's the mind-blowing part. Because of the expansion of space, those galaxies are actually much farther away now than they were when the light we see today left them. In fact, astronomers estimate that the edge of the observable universe is currently about 46.5 billion light-years away from us. This discrepancy arises because the expansion of the universe has been accelerating over time. So even though we can only see light that has had time to travel to us since the Big Bang, the objects that emitted that light are now much farther away due to the ever-expanding fabric of space. The boundary of the observable universe is often referred to as the cosmic horizon. It's not a physical barrier, but rather a limit on how far we can see. Just like the horizon on Earth, which isn't the edge of the planet, but simply the farthest we can see due to the curvature of the Earth, the cosmic horizon is the farthest we can see due to the finite speed of light and the expanding universe. Anything beyond the cosmic horizon is currently invisible to us. The light from those regions hasn't had enough time to reach us since the Big Bang, but while the cosmic horizon limits our view, it also sparks our imagination. The observable universe may be vast, but it's just a glimpse into the grand tapestry of the cosmos. The observable universe isn't just a random scattering of stars and planets. It's a structured and awe-inspiring tapestry woven together by billions upon billions of galaxies. Galaxies are vast islands of stars, gas, dust, and dark matter, held together by gravity. They come in a variety of shapes and sizes, each with its own unique story to tell. Some galaxies, like our own Milky Way, are spiral galaxies. These majestic structures resemble giant pinwheels, with graceful arms spiraling outwards from a central bulge. The arms are bustling with star formation, where clouds of gas and dust collapse under their own gravity, igniting new stars. Other galaxies, known as elliptical galaxies, are more rounded and less structured. Within these galactic islands, stars are the fundamental building blocks of light and matter. Stars are born within dense clouds of gas and dust called nebulae. These stellar nurseries are scattered throughout galaxies, glowing with an ethereal beauty as they cradle the birthplaces of stars. As gravity pulls the gas and dust in a nebula closer together, the temperature and pressure at the center increase. Eventually, the core becomes so hot and dense that nuclear fusion ignites, marking the birth of a star. Stars spend the majority of their lives fusing hydrogen into helium in their cores, releasing the energy that makes them shine. But stars don't live forever. Some stars end their lives in spectacular supernova explosions, scattering their enriched material back into space. While stars and galaxies are the visible components of the observable universe, there's an invisible force at play that shapes its structure and evolution: dark matter. Dark matter is a mysterious substance that doesn't interact with light, making it invisible to our telescopes. We can, however, infer its presence through its gravitational effects on the visible matter we can see. Observations of galaxy rotation curves, the speeds at which stars orbit around the centers of galaxies, provide some of the strongest evidence for dark matter. These observations show that stars in the outer regions of galaxies are moving much faster than they should be if they were only influenced by the gravity of the visible matter. In fact, astronomers estimate that dark matter makes up about 85% of the total mass of the universe. Galaxies themselves aren't randomly scattered throughout the observable universe. They're organized into a vast cosmic web of filaments, sheets, and voids. These structures, formed by the gravitational pull of dark matter, resemble a giant cosmic spiderweb, with galaxies clustered along the filaments and relatively empty voids in between. The cosmic web is a testament to the intricate interplay between gravity and the expansion of the universe. Understanding the distribution and evolution of these cosmic structures provides astronomers with valuable clues about the nature of dark matter, the history of the universe, and the processes that drive galaxy formation. It's a reminder that the observable universe is not a static picture, but rather a dynamic and ever-evolving cosmic dance. Imagine trying to understand a distant city without ever setting foot in it. Similarly, astronomers face the challenge of studying the vast expanse of the observable universe without ever leaving our cosmic neighborhood. Fortunately, we have cosmic messengers that bridge these vast distances: light and radiation. Light, in all its forms, from visible light to radio waves and gamma rays, carries a wealth of information about the objects that emit it. By studying this light, astronomers can unravel the secrets of distant stars, galaxies, and even the universe itself. Just like a prism splits sunlight into its constituent colors, astronomers use instruments called spectrographs to split the light from distant objects into its different wavelengths. To collect and analyze this faint light from distant objects, Astronomers rely on telescopes. Telescopes are essentially giant light buckets, designed to gather as much light as possible from distant objects and focus it into a sharp image. The larger the telescope's mirror or lens, the more light it can collect, allowing astronomers to see fainter and more distant objects. Early telescopes, like the one used by Galileo Galilei, used lenses to bend and focus light. Modern telescopes, however, primarily use mirrors to reflect and focus light. High-altitude locations, like mountaintops, are also preferred, as the thinner atmosphere at these altitudes results in less atmospheric distortion. Beyond the visible multi-wavelength astronomy, while our eyes can only see a small portion of the electromagnetic spectrum, visible light, the universe is alive with radiation at all wavelengths. To get a complete picture of the cosmos, astronomers use telescopes that can observe light across the entire electromagnetic spectrum, from radio waves to gamma rays. Radio telescopes, for example, detect radio waves emitted by a variety of objects in the universe, including pulsars, active galaxies, and the cosmic microwave background radiation, the faint afterglow of the Big Bang. Infrared telescopes can see through clouds of gas and dust, revealing star-forming regions and the centers of galaxies that are hidden from view in visible light. By combining observations from telescopes operating at different wavelengths, astronomers can gain a more complete and nuanced understanding of the universe's most extreme and enigmatic objects and phenomena. Cosmic time machines, looking back in time. One of the most remarkable aspects of studying the observable universe is that we're essentially looking back in time. Because light takes time to travel across vast distances, the farther away an object is, the longer it takes for its light to reach us. This means that when we observe distant objects, we're seeing them as they were in the past, not as they are right now. For example, when we look at the Andromeda Galaxy, our nearest galactic neighbor, we're seeing it as it was about 2.5 million years ago. This ability to look back in time allows astronomers to study the evolution of galaxies, the formation of the first stars, and even the conditions in the early universe. The expanding universe, a paradigm shift. For centuries, the prevailing view of the universe was one of immutability and permanence. The heavens were seen as a fixed and unchanging realm, a celestial sphere dotted with stars. However, in the early 20th century, this static picture of the cosmos was shattered by a revolutionary discovery. The universe is expanding. Edwin Hubble meticulously measured the distances and redshifts of galaxies and discovered a remarkable correlation. The farther away a galaxy is, the faster it's receding from us. It was a paradigm shift in our understanding of the cosmos, implying that the universe had a beginning, a moment in time when everything was much closer together. If the universe is expanding, then it stands to reason that it must have been smaller and denser in the past. Extrapolating this expansion backwards in time led physicists to propose the Big Bang theory, which posits that the universe originated from an extremely hot and dense state about 13.8 billion years ago. One of the most compelling pieces of evidence supporting the Big Bang theory is the cosmic microwave background radiation, or CMB, a faint afterglow of the Big Bang that permeates all of space. The CMB was discovered serendipitously in 1964 by astronomers Arno Penzias and Robert Wilson, who were initially puzzled by a persistent noise in their radio antenna. This noise turned out to be the faint echo of the Big Bang, radiation that had been traveling through the universe for billions of years, gradually cooling as the universe expanded. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang, a time when the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely for the first time. While the discovery of the expanding universe and the CMB provided strong support for the Big Bang theory, astronomers in the late 20th century were in for another surprise. Observations of distant supernovae, exploding stars that serve as cosmic distance markers, revealed that the expansion of the universe is not slowing down, as might be expected due to gravity, but rather accelerating. This unexpected acceleration implies the existence of a mysterious force dubbed dark energy that is counteracting gravity on cosmic scales, pushing galaxies apart at an ever-increasing rate. The nature of dark energy remains one of the biggest mysteries in modern cosmology, and its discovery has profound implications for our understanding of the fate of the universe. Current estimates suggest that dark energy makes up about 70% of the total energy density of the universe, while dark matter accounts for another 25%, leaving only about 5% for ordinary matter, the stuff that we're made of and that we can see with our telescopes. Unraveling the mysteries of dark energy and dark matter is one of the most pressing challenges facing astronomers today. The early universe, shortly after the Big Bang, was a vastly different place than the cosmos we observe today. It was a hot, dense soup of elementary particles, devoid of stars, galaxies, and the complex structures we see today. Understanding how this primordial soup evolved into the structured universe we inhabit is a central question in astronomy. Astronomers believe that the first stars, known as population 3 stars, formed a few 100 million years after the Big Bang from the primordial hydrogen and helium that filled the early universe. These stars, much more massive and short-lived than stars forming today, played a crucial role in enriching the early universe with heavier elements, the building blocks for future generations of stars and galaxies. The quest to observe these first stars and galaxies, a period known as cosmic dawn, is a major focus of current and future astronomical observations. New telescopes, both on the ground and in space, are being designed with the sensitivity and resolution needed to peer back in time to this early epoch, promising to revolutionize our understanding of the universe's infancy and its remarkable evolution. As we've journeyed through the vast expanse of the observable universe, from our humble cosmic address to the echoes of the Big Bang, we've encountered mind-boggling scales, awe-inspiring beauty, and profound mysteries. The sheer size and scope of the cosmos can make us feel incredibly small, a fleeting speck in the grand scheme of things. But instead of diminishing our significance, this cosmic perspective should fill us with a sense of wonder and interconnectedness. We are, after all, made of star stuff. The very atoms in our bodies were forged in the hearts of stars that lived and died billions of years ago, their enriched material scattered back into space, eventually becoming part of the planets, the stars, and the galaxies we see today. This cosmic connection reminds us that we are not separate from the universe, but rather an integral part of its intricate web of energy and matter. The same laws of physics that govern the motions of galaxies also govern the behavior of atoms in our bodies. The same forces that drive star formation also shape the planets and moons in our solar system. We are, in a very real sense, children of the cosmos. As we've journeyed through the vast expanse of the observable universe, we've encountered mind-boggling scales, awe-inspiring beauty, and profound mysteries. The sheer size and scope of the cosmos can make us feel incredibly small, but this cosmic perspective should fill us with a sense of wonder. We are, after all, made of star stuff. The very atoms in our bodies were forged in the hearts of stars, their enriched material scattered back into space, becoming part of the planets, stars, and galaxies we see today. This cosmic connection reminds us that we are not separate from the universe, but an integral part of its intricate web of energy and matter. While our exploration of the observable universe has revealed a great deal about its structure, history, and evolution, it has also raised new and even more profound questions. What is the nature of dark matter and dark energy, the invisible forces that shape the cosmos on the grandest scales? What lies beyond the cosmic horizon, the boundary of what we can currently observe? Are there other universes, other dimensions beyond our own? These questions, once the realm of science fiction, are now at the forefront of scientific inquiry. New generations of telescopes, both on Earth and in space, are being designed to probe these mysteries with unprecedented sensitivity and resolution. The James Webb Space Telescope, launched in 2021, promises to revolutionize our understanding of the early universe, peering back in time to the era of the first stars and galaxies. The Large Synoptic Survey Telescope, currently under construction in Chile, will scan the entire sky every few nights, creating a vast cosmic movie that will allow astronomers to study transient phenomena like supernovae, gamma-ray bursts, and even potentially new and unexpected celestial objects. The quest to understand the universe pushes the boundaries of human knowledge and ingenuity. Space exploration drives innovation in technology, engineering, and mathematics. From new materials and energy sources to advances in computing and communication, space exploration is a catalyst for progress. The spirit of curiosity and innovation drives us to explore the cosmos, seeking answers to the universe's profound questions. The universe continues to surprise and amaze us. Our journey through the cosmos is just beginning. The cosmos is calling, and we are ready to answer.